Alright, welcome back. We are moving on to section 2-3, the limit theorems. So we're just going to look at ways that limits are combined. Now, it's just a series of ways that this works out. So we're going to look at an example, talk about the various limits theorems, and then look at a final example. So, we have various rules that we have to figure out. We have to figure out how limits compare when we are adding, subtracting, multiplying, or dividing functions. So let's just look at a simple example. We're going to look at the limit of a product of two functions. Now, let's say we have g of x is 2x plus 1, f of x is 5 minus x. And actually the book uses h of x here, so I'm going to change that to an h. Just in case you're following the book, it's more closely matched. So we have h of x equals 5 minus x. Now, we have f of x is g of x times h of x. So that's going to be 2x plus 1 times 5 minus x. So this is a simple quadratic if we were to FOIL it out. I'm not going to right now. Now, what if we want to have the limit of f of x as x approaches, let's see, the book uses 3. So over here, if we plug in 3, we're going to have 2 times 3 is 6, plus 1 is 7, 5 minus 3 is 2, so it's 7 times 2 equals 14. Now, different way to look at this is the limit as x approaches 3, and instead of f of x, I'm going to write g of x times h of x. So in brackets, g of x times h of x, because that's really what f of x equals. Now, according to our rules, I am able to split this up and say this is going to be the limit as x approaches 3 of g of x times the limit as x approaches 3 h of x. Now if I plug 3 into g, 2 times 3 is 6, plus 1 is 7. Plug 3 into h, 5 minus 3 is 2, 7 times 2 is 14. It matches our original limit. So for multiplying functions, we can just take the limit of the individual functions and then multiply them together. You do not have to do it like this, but the rule says that it works both ways. Now, we're going to use this idea and kind of just fast forward a little bit. If you look on page 42, there's a whole section where it says the limit theorems. Now, the limit theorems is just a collection of ideas along this line. Now, I'm not going to go into proving these, but these are very helpful in what we are currently looking at. So we have the product or multiplication like we just looked at. And I'm just going to write these down. The limit as x approaches c of gx times hx equals the limit x approaches c gx times the limit x approaches c hx, which is the two limits L1 multiplied by L2. A sum, which would be addition, so we have limit x approaches c of g of x, and we're going to say this time plus h of x, is the same thing as the limit x approaches c g of x plus limit x approaches c hx, which is our two limits added together. Now, I'm not going to do subtraction because it's just the same thing as addition, but with a negative, it works the same way, a minus and minus. Same thing with division. Now, a division sign would just replace multiplication and be divide, divide. The only issue is sometimes you'll end up dividing by 0. So we'll make sure we look out for that if that happens. But I'm not going to go ahead and write them down. One more rule we're going to look at for now is limit of a constant times a function. So I'm just going to put down constant multiplication. Now this is a good rule to have as well. So let's say I want the limit as x approaches c of some constant k times g of x. Now, our rule says that we can pull that constant out and multiply it by the limit. So I don't have to worry about the constant until I'm done with the limit. So this is going to be k times, I think it was L1 we used for g of x. So it's pretty simple. Okay, multiplication you can split them apart. Addition you can split them apart. Same thing for division and subtraction. A constant multiplication, you can pull the constant out. So these are ways that we can simplify the situation so that a problem is not very difficult. Now, let's take a look at this in the example at the bottom of that page. So we have example 1, and this is on page 42. It says use the limit properties to prove this. Limit as x approaches 3, we have x cubed minus x squared minus 2x minus 12 over x minus 3. And it says prove that equals 19. Well, the problem is, if I plug in 3, 3 minus 3 is 0, the bottom's 0. However, what happens in the top? So I'm just going to write f of 3. We know the bottom is 0. What's the top? 3 cubed is 27, minus 3 squared, so minus 9 is 18, minus 6 is 12, minus 12 is 0. 0, 0 means it is indeterminate form. Now remember from a previous lesson, indeterminate form, I'll write that, indeterminate means we have a removable discontinuity. Now, the difficulty is going to lie in how do I remove x minus 3 from the top? I need to factor a cubic, which isn't always easy. Now, the book has you walking through something called synthetic substitution. Not really my favorite. I like to use what I call, or what is called, either synthetic division or long division. Now, this is really, really long division as compared to usual long division. So we'll call it synthetic division. We are going to take the top, x cubed minus x squared minus 2x minus 12. We are going to divide it by x minus 3 and see what's left. So, I need to turn x into an x cubed. To do that, I multiply by x squared. I'm going to write it here so I keep stuff lined up. X squared times x is x cubed. X squared times negative 3 is minus 3x squared. I take that, subtract it from above. X cubed minus x cubed is 0. Negative x squared minus negative 3x squared is 2x squared because minus negative. And then I'm going to bring down the minus 2x. To turn x into 2x squared, I need to multiply, whoops, that was a mistake, let me get rid of that. Need to multiply by a 2x. 2x times x is 2x squared. So, 2x squared, 2x times negative 3 is minus 6x. Take it and subtract it. 2x squared minus 2x squared gets rid of it. That's what our goal was. Negative 2x minus negative 6x is 4x because a minus negative turns positive. Bring down the minus 12. I need to turn x into a 4x, so I multiply by 4. 4 times x is 4x. 4 times negative 3 is minus 12. Now the goal, if we did this correctly, is everything cancels out, no remainder. This is what's left on top. So my factoring, the cubic, says x minus 3 and x to the third minus x squared minus 2x minus 12. Whoops, I just wrote the same thing again. My bad, let me get rid of that. Because it should be x minus 3, and then on the inside is what our answer was just now. So let me fix that. So x minus 3, and then this is what I want. Otherwise, there was no point in what we just did. X squared plus 2x plus 4. And then this is over x minus 3. Those cancel. That was our removable discontinuity. We removed it. So now our newly defined function is x squared plus 2x plus 4. So f of 3. 3 squared is 9, plus 6 is 15, plus 4, 19. We have proven that the limit is 19 using the removable discontinuity. Now, that's that example. I'm going to go ahead and pull out some problems from the problem set and start working on those.